Lesson 5 is dedicated to Newton's second law of motion. We will deduce how the net force causes objects to move. Remember to download your free copy of the study guide. The link is in the description below. Let's begin today's lesson. Newton's second law of motion states that the net force acting on an object causes the object to accelerate. The acceleration of the object is directly proportional to the net force acting on it and inversely proportional to its mass. Now, to fully understand this law, consider an object that moves along a horizontal surface. Let's say we have a car that experiences the net force in this direction. Remember that the net force is the vector sum of all the forces acting on an object. Please be sure to check out lesson 1 where we explain the net force. So this net force in this situation will cause the object to have an acceleration A. Remember that the acceleration is the rate of change of velocity. That means we look at how the velocity changes from the initial velocity to the final velocity over time. We look at how the object changes its velocity from the initial velocity to the final velocity over time. T final minus T initial. Now we're saying here with Newton's second law that this acceleration is directly proportional to the net force, meaning that if the net force is increased, the acceleration will also increase with the same ratio. So if I double the net force, the acceleration will also double. If I take 1/3 of the net force, the acceleration will also reduce by 1/3. We also say again that the acceleration is inversely proportional to the mass. This means that a big object will have a small acceleration compared to a small object which will have a higher acceleration. But also from this law we notice that it is possible to have objects that are big to actually move at a higher acceleration. This can be achieved by increasing the net force when we're dealing with a big object, because when we increase the net force, the acceleration will also increase. And vice versa, it is also possible to move a small object at a low acceleration by applying a small net force. Remember, the net force is directly proportional to the acceleration. The symbol for the net force is N2. This relationship that I've explained here, the direct proportion and inverse proportion between the acceleration and the net force and the acceleration and the mass, can be written mathematically as an equation that says the net force is equals to m times a, where the a stands for the acceleration, as I've defined it here to say the acceleration is the rate of change of velocity. So this means the acceleration is measured in SI units of meters per second squared or meters per second per second. The mass is represented by the symbol m and is measured in kilograms. Remember, in the previous lessons we talked about the mass and defined the mass to say the mass is the measure of inertia. Please refer to lesson 4 to go back and review, or if you've skipped that lesson, you might go back there. We define what the mass is. And F net is the net force acting on an object. And we already know from lesson 1 when we introduced the net force that it is measured in newtons. And also it is important to notice from this equation that if I were to substitute the SI units here, I will have kilogram meters. I'll have kilogram meters per second squared. So that means 1 Newton, because we're saying force is measured in newtons, is exactly the same as 1 kilogram meters per second squared. Now you would see from this equation that the mass, when we deal with our problems, is a quantity that does not change. It remains constant. It is a quantity that does not change. It will remain constant. So what I'm saying is that if this object on the side accelerates on the horizontal surface like that, its mass will never change. It will remain the same throughout the motion. We don't study deformable systems. So this object won't deform. It will remain like that with its mass. Now, this allows from this equation the direct proportion relationship between mass and acceleration to take place. This allows that if the net force increases, the acceleration to also increase, or if the net force decreases, the acceleration to also decrease, because this will be a constant. It's like we call it a constant of proportionality in that equation. Another interesting thing to observe about this equation is that it represents a resultant vector. This equation F net is equals to ma represents the resultant vector. That means that it has the x and the y components respectively. So this means when we use this equation, we will apply it in the x direction and the y direction separately. I see here I made a mistake when I typed the study guides. It should be Fy there. Now to explain this, let me go back to this diagram. Remember, if I were to look for the forces acting on this object that makes up the net force, you would see that it will be the force of the engine of the car. Let me erase this net force here. What we'll have here is that we'll have F. So this is the applied force by the engine of the car, is the force that the engine applies on the car to try to move, to make it to move to the forward direction, to the right direction. But at the same time, we know that this object moves on a surface, so there must be some form of friction, kinetic friction. Now, if I were to apply Newton's second law in this scenario, I would say the sum of forces in the x, because remember, I'm in the x direction. Remember that, let me use the reference frame to show direction. Remember that we have x and y direction. This means that anything that is along the x-axis and is going to that direction is positive to the right, and anything that will go in that direction is negative. Now anything that is in the y direction and goes up will be positive, and anything that goes down will be negative. That's how I choose my direction then. Now when we apply Newton's second law, we're going to look at the x component. This is the x component. I'll add the forces that are in the x component. So this means I will say F, which is this force here, it's positive because it's going to the positive direction. And I would say here plus, but also I'll subtract Fk, the frictional force here, because it's going in the negative direction. And we know that the positive and the negative will give me a negative, so we'll end up having F minus Fk. But according to Newton's second law, we just said that this net force here, which is the difference of these two forces, is equals to the mass times the acceleration. But the acceleration we're referring to is the acceleration in the x direction, in the horizontal direction, is the acceleration that the object has as it's moving towards that direction. In the same sense, so I've applied Newton's second law in the x component. But we also know that this object will experience the force of gravity. We know that this object will experience the force of gravity in Fg, in the vertical direction. And also there will be some form of normal force here. Okay, my normal force should be vertically straight. It shouldn't be inclined like that. So we also know that we'll have the normal force. Now, if I take the y component, meaning I add the forces in the y direction, you would see that I'll have the normal force being positive because it goes up. Then we would have here would have a plus minus Fg because it's going in the negative direction. But the plus and the negative will give us a negative. So we'll have F negative Fg there. And this is equals to mass times acceleration in the y direction. Now, it is important to note that the acceleration in the y direction, if I were to draw the acceleration in the y direction here, we actually do not have acceleration in this direction. It is 0 meters per second squared. So the acceleration, in fact, I shouldn't even draw the arrow there because there is no magnitude. The acceleration in the y direction is 0 meters per second squared. The reason being is because this object does not go up or even down. It does not move in that y direction. It only moves in the x direction. So there's no change in velocity in terms of it going up or down. It only moves horizontally. So this means that when you look at this equation here, we'll end up having normal force minus Fg is equals to mass times 0. And this means that we'll have this equals to 0 because m times 0 will just give you a 0. So that's how the Newton's second law should be applied. You need to apply it separately in the x and in the y direction. Now, the conclusions that we learn from Newton's second law is that for an object to change its motion, there must be a net force. For an object to change its motion, there must be a net force. A net force is responsible for causing a change in motion. So to go back to this diagram that I'm using in this side, is to say that for this object to have an acceleration, for it to move, it is not caused by this force. It is caused by this force and this force combined, giving us the net force. Hence I said for you to have an understanding of this, please refer to lesson 1 where we've broken down the net force and what it means. So the combination of these two forces are the ones that cause an object to accelerate, because when you combine these two, we get the net force. And according to Newton's second law, we're saying this net force is directly proportional to the acceleration, is the one that causes the object to accelerate. Very important not to confuse that, right? There are cases where you find that the net force and the applied force are the same. So for instance, if we say the surface is frictionless, there's no friction, it means this force is not here. And when you add the forces, you'll find that the only force present is this one. You'll only be putting this force. Then it means this force causes an acceleration. But in general, no one single force can cause a change in motion, but actually it's the net force that causes a change in motion. The other conclusion that we have to see from Newton's second law is the fact that the net force and acceleration, they are always in the same direction, right? This follows from the fact that the two are directly proportional. So what we're saying here is that if the net force is going in that direction, the acceleration should also go in that direction. It is not possible for the net force to go in this direction and the acceleration to go in that direction. It cannot happen because they are directly proportional. So the net force and the acceleration are always in the same direction. Another important term to know that goes hand in hand with Newton's second law is equilibrium. Equilibrium is a special situation where the acceleration and the net force are both zero, right? They are both zero. The net force is zero and the acceleration is zero, right? Remember, with Newton's first law, we said that it is possible for an object to continue moving at a constant velocity, right, if there is no net force. So when you think of equilibrium, do not only think of objects that are not moving. It could be that it's an object that there's forces acting on it, and those forces are equal and it does not move. But at the same time, it could be that the object actually moves. So I'll just draw another diagram quickly here. I'll draw a box too. I think it's important to make this point very clear. If we have a box here and we pull in this box with a force F, and there's some frictional force that the box experiences here, right? And the box does not move, it means this force will be static friction force. And this means that if I'm looking for my net force, for this object not to move, it means these two forces must be equal. Because if this is greater than this, then the object will move in that direction. It will have an acceleration, right? So for them to be equal, it means this object does not move. So this means that if here I say F minus Fs, I should get a 0, right? Because the net force is 0, it means also that the acceleration in this case is also 0 meters per second squared. But also it's possible, let's say you have an object that moves at a constant velocity or speed. So let's say we have a car here, right? And this car moves at a constant velocity. This means that the initial velocity, let's say we give it a value v, right? V could represent any number. But now when this car gets to this point, let's say this car gets to this point, right? So it will have some final velocity v final. Because it's a constant velocity, we're saying it's a constant velocity of speed, it means it will still be v when it gets here, because constant would mean that it is uniform, it does not change. So what we started with here, a velocity of v, at some later time there, when the object is somewhere here, it will still be v, right? If this is 2 meters per second, it will still be 2 meters per second. If this is 50 meters per second, it will still be 50 meters per second. Now, if we were to calculate the acceleration of this object here, we will say that it is the final velocity minus the initial velocity over the change in time. Now, our final velocity is v, right, this one here, and our initial velocity is also v, this one here. So we'll substitute v there, and then we have change in t, right? Now v minus v will give me a 0, so that I then now have the acceleration is equals to 0 meters per second squared, because any number divided by 0 is when we're doing a division by 0, if we divide 0 by any number, we get a value of 0. Now, because the velocity is 0 here, it means the net force is also 0 newtons. So it means what I'm trying to conclude is that if an object moves at a constant speed or velocity, the acceleration will always be 0. And if the acceleration is 0 from Newton's second law, we know that the net force will also be 0, right? Even Newton's first law assists us to explain this, to say, because we said in Newton's first law that an object will remain moving at a constant velocity on a straight line unless acted on by an unbalanced force. And when we did the conclusions from our previous lesson, we said, moving at a constant speed means that the acceleration is 0, and that means also that the net force is 0. So if an object moves at a constant speed or velocity, it means it is in equilibrium, right? Because both the net force and the acceleration are 0. Thank you so much for tuning into this lesson. See you in the next lesson. May the force be with you.